Chapter 10, Controlling Microbial Growth in the Body, Antimicrobial Drugs. The overview for this chapter is we're going to cover the history of antimicrobial agents, the mechanisms of antimicrobial action, clinical considerations in prescribing antimicrobial drugs, and resistance to antimicrobial drugs. Now, because the first topic, the history of antimicrobial agents, is so short, we're going to go right into that. So, Chapter 10, the history of antimicrobial agents. The learning objectives for this topic are: describe the contributions of Paul Ehrlich, Alexander Fleming, and Gerard Dominic in the development of antimicrobials. Explain how semi-synthetic and synthetic antimicrobials differ from antibiotics. So, the subtopics of this topic are: we're going to talk about some terms. We're going to talk about the state of treating infections previous to the 20th century was. We're going to talk about Paul Ehrlich, Alexander Fleming, Gerard Dominic, and antimicrobials today. So, before we get into the history of antimicrobials, it's good to discuss some terms. First off, let's talk about what we mean by the term drugs. Drugs are any chemicals that affect the physiology in any manner. So that can include food, caffeine, methamphetamines, you name it. Generally speaking, when we talk about drugs, we don't include foods. But we could talk about caffeine being a drug. It's a legal drug. But let's talk about chemotherapeutic agents. Those are drugs that are effective against a disease. So anything that helps against a disease is a chemotherapeutic agent. We usually shorten this to chemo when we're talking about treating cancer, so that's another use of the term to keep in mind. But there are some chemotherapeutic agents or drugs that treat diseases that are specific for infectious diseases, and those are antimicrobial agents, or more commonly called antibiotics. That's what we're going to be talking about in this chapter. Previous to the 20th century, 1/4 to 1/3 of all children died of infectious diseases, usually before the age of 5. And there wasn't much that the medical community could do about it. Even after germ theory of infectious disease was accepted, we didn't have a whole lot that we could do to treat the diseases that were killing children. I can't imagine how horrible that would be for parents. Also, I read a book, interesting book, about New England vampire traditions. Bet you didn't think New England had vampire traditions. I bet you thought they all came from Romania. But in New England, they had a twist. Basically, if somebody in the family died from getting weaker and weaker and becoming paler and skinnier, they didn't have any appetite, if somebody else in the family, after the first person died, started getting these same symptoms, they thought the first person was coming back from the grave as a spirit and sucking the life force out of the person. Now you're going, okay, Teresa, what does this have to do with the history of antimicrobials? Well, the symptomology sure looks like tuberculosis. Tuberculosis can get into the lungs, form tubercles, or little cysts. That's why we call it tuberculosis. And it can live dormant for years until the immune system drops. And you also pass the TB bacterium when you're living in close contact, i.e. in a family. So if you have stressors that are going to lower your immune system, say the harvest hasn't been so good, so nobody's eating very well, lost another family member to some other infectious disease, and so grieving can lower your immune system. And one person dies, another person is under the same stress, they start exhibiting tuberculosis symptoms. And so people would dig up the first person that had died of this wasting disease and do various things to keep him in the grave and not coming back, which probably further spread the TB. That just goes to show some of the things that people would do to prevent infectious disease, especially when they didn't understand where they were coming from. So let's talk about contributions of people who led to the advent of antimicrobials that gave us half a chance against infectious diseases. First off, Paul Ehrlich, who in 1908 proposed the term chemotherapy, the idea that chemicals could kill pathogens with little or no effect on the patient. He actually got the idea from the Gram stain, where one stain appeared to be attracted to one type of bacterium and another stain, actually a counter staining, would be attracted to another bacterium. So he got the idea, well, what if we could get poisons that would go just to the pathogen and leave the patient alone? And through his work in chemotherapy, he discovered some arsenic compounds that worked against sleeping sickness, which is a trypanosome parasite, and syphilis, which is caused by a bacterium called treponemia. And so he did have some success with his ideas. Unfortunately, arsenic compounds have some severe side effects. So when using arsenic-containing compounds, you have to balance toxicity to the pathogen versus side effects to the patient. In other words, you want to kill the microbes, you don't want to kill the patient. So these compounds were not widely used, they were kind of a last resort. Now on to Alexander Fleming. In 1929, you probably have heard of the famous experiment where he had been growing some Staphylococcus aureus and had left some plates to incubate over the weekend, and when he came back, one of them had mold growing on it, and around the mold there was an area of death or inhibition of the bacteria colonies. Well, this got him thinking that this could be a chemotherapeutic agent, and we now know this as penicillin. And penicillin acts against the cell walls of bacteria and is produced by the penicillium mold. This was used widely for about 20 more years because wild-type penicillium doesn't produce all that much penicillin, not enough to be clinically effective. So we had to grow penicillium in the lab and basically breed a strain that produced high amounts of penicillin so that we could do this industrially and make it available to large numbers of patients. On to Gerald Dominic, who in 1932 discovered the first sulfa drug. Basically, what happened is there was a red dye that the Germans were making synthetically that they found was effective in treating pneumonia in lab animals, and then they moved to, their equivalent of clinical trials at the time, and found that it inhibited bacterial growth. And it was the first routinely used antimicrobial. Because it could be made synthetically in the lab, we could make it in large quantities industrially and make it available to lots of different people. Later on we found out that it inhibits folic acid synthesis, and we'll talk more about that in later topics. So nowadays we have lots of antimicrobials available to us, and they come in three classes. There's the natural, which is the chemical exactly how it's made by the microbe. So we have two molds listed here, Penicillium and Cephalosporum, that produce antimicrobials for us. There's also two genuses of bacteria, Bacillus and Streptomyces, that produce antimicrobials for us. So looking at this structural formula down here, penicillin G is the natural. Bacteria produce an enzyme called penicillinase or beta-lactamases that clip this beta-lactam ring, and so it inactivates penicillin. So what we've done is we've developed semi-synthetics like methicillin, where basically we take penicillin G and in the lab we add some side groups that protect the beta-lactam ring from penicillinase. Of course, the penicillinase can be modified so that it can inactivate methicillin, and it's kind of an arms race. Now, we also have synthetics, which are like your sulfa drugs that are completely man-made, and we make them in the lab. They're not based upon a natural product. Well, that's it for this topic. Here are reminders of what you need to learn from this topic, and we'll go on to the next one.